The Milky Way will stop making stars, and hardly anyone will notice. Galactic death is quiet, like a city running out of lights. In plain terms, star birth shuts off as fuel runs dry. The immediate takeaway is simple: no cold gas means no stars. That silence spreads from the center, then creeps across the disk. You still see starlight, but it grows redder and older. Today we can watch galaxies dim, almost in slow motion. We can measure the leaks, the heat, and the missing fuel. Picture a blue spiral, its arms dotted with young, hot clusters. A few billion years pass and the blue fades to rust. That slow color shift signals quenching, the shutdown of star formation. It matters because the galaxy's future shape and brightness are decided. Stars stop being replaced, so the population grows old and dim. Here is how the light switch gets turned down across space. Gas must cool, collapse, and fragment before any star can ignite. Heating, stirring, or removing that gas breaks the star factory completely. A galaxy can burn fuel faster than new fuel flows in. Dark matter halos can also keep gas hot, blocking fresh clouds. Once the supply thins, gravity loses the race against pressure. Clouds fail to collapse, so nurseries close, sometimes from inside out. Quick check: if blue patches vanish, the factory is going offline. Take a mid-mass spiral making 5 suns each year today. Over 2 billion years, that rate can slide to a tenth. Its spectrum reddens as short-lived blue stars die without replacements. The arms look smoother, while dust lanes soften and break apart. Neighbors might call it Green Valley at first, then fully red. Central bulges grow as bars drive gas inward, then heat it. With fewer massive stars, ultraviolet light drops and cooling becomes harder. For that same spiral, cold gas might fall from 10 to 5%. Star formation would then take 10 gig-years to exhaust the leftovers. Astronomers would plot it sliding off the star-forming main sequence. So the picture is straightforward: lose cold gas and quenching follows. Far outside the disk, pale rivers of gas thread the dark. They flow along filaments, feeding the halo like veins. That supply chain is the universe's tap for star formation. Care matters here because when the tap tightens, factories idle. Galaxies cannot build stars from nothing, they need fresh, cold atoms. As the universe expands, densities drop and inflow weakens steadily. In massive halos, infalling gas shocks to the virial temperature. Hot halos hold pressure, stopping clouds from cooling fast enough. Ultraviolet background light also keeps small systems warm and puffy. Mergers can add fuel, but they also heat what they deliver. The balance becomes a budget between inflow, outflow, and consumption. If inflow dips below consumption, reservoirs shrink year after year. Cooling delays then stretch from millions to hundreds of millions. Eventually, clouds cannot reach the densities needed for collapse. Example in real terms, consider a halo near 1 trillion suns. Cold streams reach the center at early times, feeding bursts. By today, shock heating dominates and the streams stall outside. Accretion rates can fall by half every few billion years. A disk once forming 5 suns yearly drops near 1. Its gas fraction declines, so turbulent support beats self-gravity. Observers see this as fewer blue knots and weaker hydrogen glow. Deep radio maps reveal thinner reservoirs of atomic and molecular gas. X-ray halos brighten slightly, hinting more heat locked in place. So the net effect is a slow strangulation of star birth. Now drop that galaxy into a crowded cluster, moving at breakneck speed. Hot plasma fills the cluster, thin as smoke but incredibly fast. Ram pressure stripping is the wind that tears gas from disks. It matters because one pass can slash star formation dramatically. A single encounter can set the clock for permanent quenching. As the galaxy plows ahead, pressure builds on its leading face. Diffuse gas lifts first, then dense clouds peel from the outskirts. Magnetic fields stretch, and turbulence wakes trail behind the disk. New inflow from outside gets cut, a process called strangulation. Repeated orbits compound the damage, shaving the reservoir each time. Shocks in the wake also drive outflows that never fall back. Tiny test: if you see a tail, the wind is winning. Stars remain bound, but their nurseries stream away like ribbons. Centers can stay active briefly, protected by gravity's deeper well. Over time, the wind eats inward, then the lights go amber. Real cases look dramatic, like jellyfish galaxies with 100,000 light-year tails. NGC 4522 in Virgo shows stripped dust and truncated arms. Its star formation dropped within a few 100 million years. Others display knots of newborn stars inside the moving gas tail. Those knots burn fast, then die, leaving the tail dark. Harassment by flybys and tides shakes disks, adding extra heat. Cluster cores finish the job with dense peaks and savage winds. When the orbits settle, the remnant glows red, smooth, and quiet. Bottom line, the environment can yank the fuel out by force. Zoom into the core where a black hole sits like a furnace. Sometimes it feeds, then it launches jets and wide, hot bubbles. This central heating is called active galactic nucleus feedback. It matters because it keeps gas hot enough to resist collapse. When the heater runs, the fridge of the galaxy shuts down. Jets tunnel through halos, inflating cavities that rise like balloons. Shocks ripple through the gas, stirring turbulence across enormous volumes. Outflows carry cold clouds outward, so far they cannot return. Radiation also ionizes gas, making cooling lines fade and stall. Together, these processes put the brakes on new star formation. Supernovae add a gentler version, pushing and heating local clouds. They punch holes in disks, letting heat leak into the halo. The combined effect is maintenance heat, not one quick explosion. Keep the reservoir warm and it refuses to make new suns. Turn it off and cooling resumes slowly if fresh fuel arrives. We measure this with spectra, images, and careful energy budgets. In Perseus, cavities mark worth about 10 to the power of 60 ergs. Mate 7 shows a jet carving channels through a bright X-ray atmosphere. Nearby galaxies host molecular outflows moving hundreds of kilometers per second. Those flows match the deficit in star formation within uncertainties. Example in numbers, consider gas mass near 100 billion suns. A jet injecting 1 to 10% of binding energy suffices. That stops cooling for hundreds of millions of critical years. So the recap is simple: heat the tank and the engine stalls. Step back and you see a smooth galaxy glowing like old coals. It has joined the red sequence, a cemetery of past fireworks. That phrase means the light is dominated by long-lived, cooler stars. It matters because the future brightness and color are now locked. The clock will only run down, never spring forward again. Massive blue stars died first, leaving remnants and enriching the gas. Without new gas, that enrichment cannot seed fresh stellar nurseries. White dwarfs cool slowly, turning from ivory to charcoal with time. Neutron stars and black holes keep orbiting, silent and hard to find. Residual gas drifts to the center, or escapes to the group. Some gas may form a trickle of stars in the core. The stellar initial mass function loads the future with red dwarfs. They sip fuel for trillions of years, far beyond cosmic now. The surface brightness fades as giants die and dwarfs hide. Metal-rich populations redden spectra and strengthen old absorption features. Globular clusters survive, while dusty lanes thin and disappear. Consider an elliptical with 100 billion to 1 trillion stars. Over 10 billion years, it can dim by a factor 10. After 100 trillion years, only faint embers remain detectable. By then, white dwarfs have cooled below today's lowest detection limits. The galaxy still exists, yet it looks like a ghost. Common mistake is thinking stars vanish. They actually outlive the fireworks. What fades is the formation line, not the inventory of stars. Net result, death means retirement from making stars, not disappearance. Now place us inside the story, under the Milky Way's arch. Our galaxy still forms stars, but the pace has slowed. Galactic death here will be gradual, not sudden or dramatic. It matters because our night sky's texture will evolve over eons. Future astronomers will witness the fade, even if we cannot. Accretion from the cosmic web is weaker today than before. Hot halo gas surrounds the disk, holding pressure against collapse. Feedback from stars and the central black hole adds gentle heat. Cold gas remains, yet reservoirs are smaller than in cosmic noon. Inside-out quenching likely continues, dimming the inner ring first. A major chapter arrives with Andromeda on a slow collision. In about 4 to 5 billion years, the disks will merge. Tidal forces scramble orbits and feed central starbursts briefly. After the fireworks, the remnant's halo gets hotter and more massive. Without fresh inflow, cooling times drift far beyond Hubble times. Simulations predict a burst, then a long decline to near zero. Star formation could sink below a 10th sun per year afterward. Gas fractions fall, while stars scatter into a puffy, smooth spheroid. The sky will show fewer blue clusters and broader milky light. The sun will be gone by then, but the trend continues. Look at analogs like galaxies already quenched in small groups. They show weak hydrogen glow, older stars, and quiet X-ray halos. So the path for us is familiar and probably unavoidable. Bottom line, the local group will settle into a long twilight. Let's zoom into a single cloud, cold, dark, and gently spinning. This is where disappearance is defined in the probability of collapse. Disappearance means births stop, not that existing stars go missing. It matters because the light you see now is a legacy. The current glow reflects history, not a promise of tomorrow. Star formation follows a rule linking gas density to birth rate. Denser gas makes more stars, roughly with a power law slope. If density falls everywhere, rates shrink across the entire disk. Turbulence, temperature, and shear each tilt the odds against gravity. Remove just a bit of pressure support, and collapse can resume. Rule of thumb, depletion time is gas mass divided by birth rate. Typical disks show 1 to 3 billion years for that clock. Starbursts burn faster in a few 100 million years. Shut the inflow, and the clock finally counts down to 0. Say you hold 1 billion suns of cold gas in reservoirs. At half a sun per year, that lasts about 2 billion years. If feedback drives a fifth of that away, the time shrinks quick. If the disk stabilizes with a bar, collapse slows even more. Maps then reveal rings of light with dark holes in between. Observers test this with hydrogen lines, dust, and carbon monoxide. They see inside-out patterns and exponential declines in rate. Galaxies peel from the main sequence toward the red sequence. Those trends match simulations within a factor of a few. What to remember, no cold gas equals no births, period. So yes, galaxies die quietly, exactly like city lights fading. The secret was never doom, it was simply missing fuel. We watch the supplies shrink, the heaters hum, and births pause. The fireworks stop first, then the embers carry light for ages. Nothing explodes at the end, the rooms just grow darker. You can now picture quenching as a budget that dries up. You know the forces: inflow, heating, stripping, and stability. You have seen the examples: clusters, jets, and long, red afterglows. And you know our home will join that quiet parade. This is the pace of cosmic living and cosmic aging. If that calm unraveling intrigues you, I would love your company. Tap subscribe if you want more deep, unhurried explorations. Next time we will chase the first sparks, not the last. Until then, keep looking up, even as the lights dim.